All right, well, hello, good morning, good afternoon, and good evening, everybody. My name is Joe Petroske. Today, we're going to be doing a few things that are going to be really fun and hopefully informative, and people will get a lot out of this. We'll be talking about hunting PowerShell obfuscation using an interesting machine learning technique called a Support Vector Classifier. Before we get into that, I just want to say a huge thank you to SANS today for making this a reality, and particularly for making the virtual conference a reality for all of us. It's a fantastic resource for all of us all around the globe. I'm a little blown away right now. Little kid me would never have believed that I would be one day doing a nerdy presentation for people all over the planet. And they're making this a reality for us today. So thank you, in particular, thank you to Carlos and Emily and Jen and Corrigan for kind of being my handler and walking me through the ins and outs of being a virtual presenter. So I will be joining you today from my home in Minneapolis, where I live with my wife, Charney, and our 3 dogs. And I'm very happy to be here with you all today. And without further ado, let's get into it. So here's what we will be talking about today. I'll introduce myself quickly, give you a little bit of background on who I am and where I'm coming from. And then we'll talk about what it is that we're actually looking for, what problem we're trying to solve here, and how we'll be trying to accomplish the solution to that problem. And I'll talk about what exactly is a support vector classifier. This is kind of the meat and potatoes and the bones behind what we'll be doing today and how we'll be solving this problem. My goal today is that whether you are a seasoned machine learning professional and been doing this for years, or you're a complete noob and have never seen this before, you'll be able to get something out of this. And that's really gets me excited. So I'm really, really thankful for all of you for coming along with this little presentation with me today. Once we get the definitions in place and talk about how we're going to solve this problem, we'll actually put in a working implementation of how to do this. And because if I'm going to do a talk with people, I want to be able to share stuff that the people will be able to take and use right away. So I'll be sharing some working code. You'll be able to take this, play it around with it, and hopefully use this in your world and get this thing, some production out of this pretty much right away. So that will be our goal for today. So here's me. My name is Joe. I've been doing blue team stuff for roughly 15 years, about the past dozen in incident response and threat hunting. That is my current gig right now. I'm a cyber threat hunter for Target, a US-based large retailer, everyone's favorite place to get stuff for their lives. I have a very cool job. I work with a team of very talented and very cool people. And in my current role, I get to do a lot of interesting things like finding new and novel ways to find suspicious and weird things that might be associated with evil activity, and seeing what to do with it there. So it's a little art, it's a little science, it's a lot of fun. I really enjoy my job. And I'm really happy to be able to share a little bit of this with you today. When I'm not doing that, I dabble as a musician. I'm a lacrosse ref. I'm kind of a crazy dog guy. So you'll probably see me doing something like that when I'm away from keyboard. Okay, so let's dig into this by kind of taking a look at why we should care about PowerShell obfuscation in the first place. And if you've done IR, or if you've even just done a quick few Google searches, you come up with all kinds of hands-on examples of PowerShell obfuscation being used by adversaries to do evil things. It's near ubiquitous as a first stage loader, just because it's so easy to use. There's not much of a barrier to entry, and it's also very easy to obfuscate. So it's very easy to take a normal PowerShell command that would do something and turn it into a mess that's not readable by humans. Because of the near ubiquity of this is something that should be on our radars as defenders, no matter what you're doing. So that's why we should care. What is it specifically that we're going to be looking for here? And we'll talk about some examples about what we might be trying to identify with a technique like this. What we're looking for is a PowerShell command that has been altered by someone to make it look like you can't read it or tell what it is that this thing is doing. And the reason for doing that is to defeat analysis by cyber defense people, such as incident responders, malware reverse engineers, security researchers, and stuff. And the reason you're doing that is because you're trying to do something evil with it. So if you're seeing obfuscated PowerShell commands in it, that should get your radar going, and that should really get you, really focused in on that as something that you really needs further attention. So here's some examples. You're going to see a lot of PowerShell in your command. If you run Windows at all, there's a lot of near ubiquity here. It's a great tool for use by administrators. You'll see this used for all kinds of different things, for job automation and just making things generally easier. So here's an example of a PowerShell command. Without further context, you can kind of look at this and go, okay, well, they're setting the color of some sort of user prompt, and without any other knowledge about the situation, you can read this and kind of tell what it is. So I would use this as an example of, this is a normal, benign, non-obfuscated command that you could have found somewhere in your environment. This looks like someone who's, some sort of programmer who is making some sort of thing to put in front of a user. So this looks like a good example. Here's something else. So the intent here is not to read this tiny type on the screen here. It's to look at it and go, like, I have no idea what this is. And that's really kind of the point. So I don't really know what this is. If you're kind of familiar with some things here, you can kind of tell that this is an invoke web request obfuscated somehow, but you can kind of piece that together just by looking at the components of this. But you can tell, like, there's a lot wrong with this. There's a bunch of strings that have been cut up into tokens and then repositioned and moved around a lot. Tokens have been split up, like strings have been cut up, put back together, escape charactered, generally twisted around. There's a lot to be done here to try to make it look like something that isn't really normally readable by a human, like such as me. So, and if you saw this in your environment, it's time to go get the IR team rolling, because we got to burn this down pretty fast. Let's talk about what our goal is going to be when we use a technique such as this for hunting. So we wouldn't necessarily be making static detection out of this. I always draw a detection or a distinction between static detection. So something happens and you alert, versus more of a threat hunting approach, which is what we're going to be doing. Whereas you take a lot of stuff down and reduce it to such a manageable level that is most likely, if there's evil stuff in here, it will be in this smaller corpus of things that you just identified. So what we're trying to do here is gather a large body of PowerShell commands that are run across your organization and boil that down into something like that we can confidently say that if there is obfuscation present somewhere in here, it's going to be in this smaller data set that a human can then go look at and pick out. Let's talk about what specifically we're going to be looking for here. So this is kind of a good thing to keep in mind when you're looking for obfuscated PowerShell. There's no way to detect every single way to obfuscate a command. So don't go into this thinking like, I need to write detection for every single way that you can potentially obfuscate a PowerShell command. There's no way to do that. This is really limited only by the adversary's creativity. So this is going to be kind of a fool's errand. Instead, what we want to do is just identify commands that are obfuscated in the first place. If something is obfuscated, it is most likely been done for that reason, so as to obscure its true meaning and what it does from defenders. So if we can just identify that something is obfuscated in the first place, that becomes our short list for further investigation. Here's how we're going to get started with this. We'll be doing this with a very interesting tooling set here. So to start with, we're going to need a body of data. To really do this at scale, you're going to need to collect PowerShell logging and script logging from across your entire enterprise. Event ID 800 or Sysmon Event ID 1 will accomplish this goal for you. This should be run anywhere you can get it from. And I realize that this can be a big lift for a lot of organizations. If you're really serious about doing hunting of this kind of stuff at scale, this is really something you need to be looking at, is collecting this kind of information and ingesting into some sort of central repository where your investigators can get it, such as a SIM or some other kind of repository for this kind of logging. The tools we're going to be running here are going to be based on Jupyter Notebook, Pandas, and Plotly Express. If you're familiar with Jupyter Notebook and are an old pro with this, you're already rubbing your hands with glee. If you haven't been using Jupyter Notebook, I strongly recommend it. It's a fantastic tool. This is a way of running interactive Python from within a browser, which is great when you're doing stuff like threat hunting, because you can get into a lot of trial and error. You try something, did that work? No. Let's try something else. Did that work? Well, kinda. Did I just code it wrong? Yes. And you continuously refine these things. And what Jupyter allows you to do is write your code in little sections at a time and get each section working, rather than having to go back and modify a large monolithic .py file or its libraries every single time you want to try it. You can just get little bits working at a time and then go from there. Pandas is a really cool data science library for Python. There's others out there. This happens to be like just my personal favorite. I use this one a lot. For a visualization engine, I use Plotly Express. Again, there's others out there. This just happens to be my personal preference. Here's where you can go to get all these things. The real reason I like using a tool set like this is because it is available for the amazing low price of free, or 4 easy payments of $0. This I'm not selling anything here. You can go get all this stuff on your own. It's freely downloadable, and the intent of this is to be able to share it. So that's what I'm going to be doing. The actual engine for doing the machine learning component of what we're about to do here is a Python library called sklearn, scikit-learn. This has a bunch of different data science and machine learning and artificial intelligence capabilities in it, built in directly in this. So someone has already written this, we might as well go ahead and use it for our advantage. So these are going to be the sort of prerequisites of tooling that we're going to use to go look for some obfuscation. So here's some operating assumptions that we'll be working under. If we're starting to talk about what evil PowerShell might look like, and if you've seen some of this stuff in the real world, you can kind of like, you can kind of sort of put some of this stuff together. Most of the early PowerShell, or evil PowerShell, will be run fairly early in the kill chain. This is normally seen done as a loader for something else. So some sort of PowerShell command runs, and it pulls down a second stage or additional tooling or something like that. It happens fairly early on. It will probably be run direct from a shell. So in other words, not from a .ps1 script on file. This will be done in memory from a shell. And we're probably talking about a user who hasn't gotten a privilege elevation yet. So it'll be running under a non-privileged context for a user. So we can use all this to kind of come up with how we're going to zero in on what we'll actually be looking for here. So this is what we're going to need to collect over as much of a time frame as you can possibly get, and indeed duplicate. We won't be, the magnitude of how many times you see something won't matter for our analysis. What we're trying to do is just come up with as much uniqueness as we possibly can. So I did this by collecting event ID 800 from across my entire enterprise for as long as I could, with a user ID defined as what one of my users would look like, and it doesn't run from a PS1 file. So that gives you a nice corpus of data, and you get that for as long as you can get. Whether if you can only get a couple days, cool. If you can get several months to years, that's amazing. So whatever you can get out of this and get from your central location where you can get this information, this is what we're going to use to both train and test our model. Here's the patterns that we're going to be looking for here, or our machine learning algorithm is going to be looking for. If we start talking about obfuscated PowerShell, what are some of these commands that have been obfuscated have in common? You're going to see a lot of encodings and decodings. So to make the strings of the command look like something that I can't read anymore, I've got to do something like take parts of it apart, encode it into something else, and do something with it. But at the end, to make it actually do anything, that long string that was encoded has to be decoded somehow so that it can be fed to PowerShell and actually execute. It's going to be illegible, which is the entire point of the exercise of obfuscating in the first place, is to make it in such a way that a defender such as myself wouldn't be able to tell what it is by reading it. The point that it's been encoded and chopped up and had a bunch of things done to it is necessarily going to make that command longer than it would have been. So the native command would have been maybe this, but the obfuscated, chopped apart, recoded in whatever string and that is finally run is probably going to be much longer because of all this. So these are facts that we can use to our advantage when we're actually looking for an obfuscated command. Here's the big idea behind all this analysis and what we're looking for. Generally speaking, the relationship between the length of the command that it gets run and the count of various characters in that command is going to be roughly linear. So as the length of the command string increases, you're going to see more alphanumeric characters. You're going to see more of every other kind of character. Really, the big relationship that you're going to see is the relationship between the length of the command to straight alphanumeric characters, A through Z and 0 through 9. As you start seeing additional characters in the character string, that becomes more and more likely to be obfuscated. You'll see a lot of things more like backticks for escape characters. You'll see all kinds of other things that are not necessarily looking like letters and digits. When you see normally a linear relationship, things that deviate from that linear relationship become our kind of interesting zone for a further scope of inquiry. So we'll be looking for kind of deviation from this. This scatter plot you see here is a 2 variable, so X and Y, right? But there's no reason that in the real world we can't use more than 2 variables. And that's what we're going to use our machine learning algorithm to do. So we can count lots of other characters too. There's a lot of other things that might be interesting. So a $, right? That defines a PowerShell variable. A backtick is an escape character in PowerShell. String literals, quotes, double quotes, the things that put things in other containers. So braces, brackets, parentheses. You can sometimes see bad guys doing stuff like just doing chaos case switching to defeat case sensitive detection. So in other words, if you've written detection for something but it only looks for lowercase, if you change the case, it might have evaded that. So you can think about all these other kind of characters that might be present in an obfuscated PowerShell command and just get the counts of those. So these all become variables in our feature set. If you're a machine learning veteran and have been doing stuff like this before, you know exactly what I'm talking about. The really cool part about using counts like this in our feature set is that you don't have to do any normalization of this data. They're all roughly in the same order of magnitude, not real big. So we don't have to do a lot of data scrubbing before we feed this to our algorithm. There's not a lot of pre-work that's going to need to be done other than just collecting the counts of these things and feeding it to the algorithm. Okay, with that in place, it's time for some machine learning. Before I get into that, I don't want to scare anybody off here first. So one of the reasons that this particular investigation has been really kind of cool is because you don't need to do this at giant scale. You don't need to start, if you're doing your first machine learning project, with huge backend infrastructure, tons of data, a lot of pre-work, you know, and a few degrees in machine learning before you even get started. This is something that can be done at very small scale. I run this on my desktop sometimes. Like it's really can be done at that small of a scale. And what this lets you do is start small and get some wins and build your confidence and go, okay, cool. This works now. What can I do next? How can I take it a little farther the next time I want to do this? So don't be scared. If you've never done anything like this before, this is going to be super easy and you'll be able to take this and kind of run with it right away and then build some wins up and go from there. So I would just kind of caution anybody who hasn't done something like this before. Here's the quick IBM definition of what machine learning is. Yeah, it's making robots think like brains, generally speaking, or as much as they can. With the idea is that over time, you can keep improving this. So that's kind of another interesting component of what we're going to be doing here is that we can reiterate this. And every single time, your model should be getting a little bit better at it and gradually improving its accuracy. So when you do this the first few times, you might get some false positives. Maybe you get some false negatives. But over time, the more data you feed this and the more you train it, the more it learns. That algorithm should get tighter and get better at what it's looking for. I want to reiterate too, like kind of what machine learning is and is not. So if you've ever like heard someone say that like threat hunting is machine learning and machine learning is threat hunting, like don't listen to them. They're probably trying to sell you something. Maybe they are. These are two separate disciplines, right? Threat hunting is a discipline unto itself, and so is machine learning. However, where these two things overlap is where really cool things start to happen, and that's where someone like me can find a lot of really cool things to do and hopefully share with other people here. So. And then a support vector classifier is a thing unto itself. So say it with a Venn diagram, like my teacher always said, this is a great way of doing it. So we'll be using a very particular implementation of a support vector classifier, which is a machine learning tool to do some threat hunting. We'll be using a supervised machine learning technique for what we're about to do here. So for those familiar with machine learning type stuff, you can have supervised and unsupervised learning. In this kind of case, we'll be using supervised machine learning. And this is based on a model where you give it the answers. So you're not telling the machines to go find all the answers. You give them the answers up first. And the goal of the machine now is to find out why those answers were the way they are. So if the machine can take a corpus of data, classify it, and then figure out why it had classified those things as they were, we can then use that for future predictions. So that's what we're going to be doing here. Is once we have our model trained, we can then feed that some uncontrolled data and say, okay, predict whether there is anything to be found in this new data that we haven't even looked at yet. What's a support vector classifier? So this is a very specific kind of machine model that, long story short, attempts to put data into one or more, well, two or more classes. And a class can be whatever you want, groups of things, however you want to arbitrarily define what a class is. In this example here, we have two classes in 2 dimensions. You can roughly categorize them as blue things and green things. Between them, there is some sort of boundary, and that's that red line that you see in here with some sort of gap around it that becomes your kind of there's a little bit of gap around it to give yourself a little bit of cushion. So you can do this in 2 dimensions. There's no reason you can't do it in more than one. So you can kind of picture what a boundary condition might look like in 3 dimensions. It would look like some sort of a flat surface that divides parts of 3 space. And then you can generalize that to additional dimensions as well. So there's no reason we can't do this in more than 2 or 3. In this case, we're going to be doing this with a lot more dimensions. These are going to become our variables, but we're only concerned about 2 classes. We have a class of things that are obfuscated that we care about, and a class of things that are not obfuscated that is normal and benign stuff that we don't care about. And that first class should be a much smaller group of things, and those are going to become our scope of inquiry for things that are most likely evil that we need to look at closer. What's a feature set? So a feature set, for those who are pros here, know exactly what I'm talking about. That is just a long, different word for it. The amount of variables that we're going to have here. So every variable here, there's no reason we have to have more than 2, X and Y. We can have a whole bunch of them. And the list of the X variables that are going to be used as the predictor for the Y is called a feature set. The Y is what is denoted as the actual result or the label of the classification that we're trying to give to whatever the data that we're looking at is. So this becomes like our answer. In this case, the result, or Y, is going to be either 1 or 0 in our case. So 1 will stand for this is obfuscated, and 0 means that it's not. Once we have our model in place, we'll have to train and test it. This is the pre-work that we're going to need to do before we can feed this thing uncontrolled data that we want to just go investigate against. So a training set is the portion of the initial data that you've collected that's going to be used to train the model. It should be roughly 80% of the initial data set that we've collected here. Not only are we going to feed it the data that we've collected, but since we also know what the answers is, we're also going to include a column here that gives it the answer, whether these things are obfuscated or not. And generally speaking, the things that you collect from across your environment should be normal, non-obfuscated. You should probably check that a little bit so you're feeding it the correct data. But then also include some things that you do want to find. So what I did was I intentionally went in and created some obfuscated PowerShell commands. I used Daniel Bohannon's invoke obfuscation and just generated a bunch of obfuscated things and appended that to my initial data set. This becomes our training. Once we have the model trained and looked at using 80% roughly of our initial data set, you can then take the remaining portion of that data and use it as a test. So feed it back to the model and make sure that it gets the results that you think it should have. This will allow us to calculate things like how accurate our training model is. So here's the initial data collection. What I did was I just went and collected a bunch of PowerShell commands from across the environment. I got, once deduplicated, roughly about 10,000 of these things over the course of, I started even just a couple of weeks just to start at small scale. And then added a column for is obfuscated, 0 or 1. At the end of this data here is a small subset of the intentional obfuscation that I put on the end of this data set so that the model has something it needs to find. To build the testing and training set, we can use Python to do this. So what this thing is doing is based on the previous research that we've been doing here is we found that the amount of various characters in a PowerShell command will have an impact on how likely that command is to be obfuscated in the first place. So as you see more things like semicolons and backticks and braces and dollar signs and things like that, the more of those things you see, the more likely that that command is going to be obfuscated. So what we can do is just allow Python to take the counts of those things, and that will automatically build our training set, or the features for our training set. So in other words, every single one of these things becomes a variable. So count of semicolons, count of double quotes, count of left brackets, etc. This is what we're going to use to train our model. So this is a job for Python's sklearn module, scikit-learn. There are some submodules of this for support vector classifier implementation specifically. That's the stuff in the red box here. Long story short, this boils down to just a couple different lines of Python. So once you feed the data to Python here, define X as your feature set of variables and Y as the expected result, you can then use the command called fit X and Y to train the model based on the data that you just gave it. And what that will attempt to do is run through, analyze all this data and figure out why things got the answers that they did and attempt to define a decision boundary between your classes. So what that will try to do is for arbitrary data, find what side of that decision boundary that data will fall onto, and then classify it as such. So in our case, we're talking about two different classifiers, is obfuscated or is not. So in whatever kind of hyperspace boundary you come up with based on our variables, this will attempt to classify what that data looks like. Since we know the answers to all the questions that we just gave the machines, we can then evaluate the results because we know what it should have found. So we can calculate how the model worked and what it did find versus the things that it should have found. The two pieces of data in question that we'll be caring about here is both the precision and the recall. So you can think of the precision as the number of things that you correctly found versus the total number of things that you do found. So that basically is a ratio of true positives found to true positives plus false positives. The recall is kind of the reverse of that. So that's the number of things that you found versus the number of things that you should have found. So in other words, this is the ratio of your true positives versus true positives plus false negatives. There's a measure kind of like how much stuff you missed. And then the F1 score is another calculation you can do as a harmonic mean of those two scores. And because we know all the answers to this, scikit-learn can just calculate this stuff for us. So this becomes how we evaluate the model that we just trained. And if we need to tweak things, add change, alter variables, we can do that based on this. So the code that I will be sharing today has had this work done before, and in my world, it works pretty well. Your mileage may vary, and feel free to tweak as needed. So at this point, we have a trained model. We've tested its results. We've gone and looked at how effective it was, maybe gone back and done some tweaking to get this thing exactly dialed in the way we wanted to. And now it's time to go apply the model to some new uncontrolled data. In other words, we're going to be actually doing hunting with this. So the point of all this is now, once our model is trained and running, we can now take a brand new corpus of data that we've just collected from across our enterprise for as far back as you want to go, and feed it to the model and use it to predict whether there is obfuscation in any of that. And again, this boils down to just a single line of Python. It's SVC's predict model down here. So what we'll do is feed new data to that and have it issue a new prediction based off our previously trained model. And then see what you get. So what my code right now does, the way it exists right now, is it consumes just a flat file, a CSV. There's no reason you couldn't alter that if you have an API key to some larger data set someplace else to go get it at rest or whatever. And it'll spit the results out into another flat file, a CSV, for a human to go look at. So in this case, me. So what I did for the last time I tried running this with an uncontrolled data set, I intentionally appended one obfuscated command on the end of it. I then went and graphed the results on the length of the command versus just the count of alphanumeric characters. And sure enough, it found the one thing that I stuck in there as obfuscated. You can see it as that red dot over there. It deviates from that linear relationship quite a bit. And you can find it. So this wound up being a very effective thing in practice. So I was pretty happy about that. And this winds up being now something that I can hopefully share. So this is kind of why this is effective. And why I love doing this kind of stuff so much is because it's fairly genericized. It doesn't care how an adversary might have obfuscated their commands. All it cares about is that it is obfuscated. It just found stuff that was consistent with being obfuscated in the first place and categorized it as such. So that's why this boils down to it. It really don't have to get into specifics about how the adversary might have obfuscated their tooling. The feature set building is kind of done automatically, and we don't need to do a lot of additional massaging to the data. We just are looking at counts of characters within strings. So we don't have things that are different orders of magnitude and have to be normalized out between the two of them. We're talking about orders of 10 to the first, maybe 10 to the second for really long ones. So not a whole lot of things here. So these are fairly close together and don't require a lot of data manipulation before you feed it to the model. And if you think about it, this is kind of intuitive, right? So if your command is obfuscated, kind of like we saw before, you're going to see a lot of weird characters in it. And the more weird characters you see in something, the less it looks like a benign, normal, human readable command. So that's why this becomes a very predictive and useful model. To operationalize it. So what I always want to ask when doing something like this is, okay, this is cool. I got it working. Now what? How do we take it forward? What's the next step? So what I have been doing from time to time is I'll just regenerate a bunch of data and just feed it back to the model and just make sure that it works, and feed it to predict and make sure that it's doing what I think it's going to be doing. What I'm going to be doing here in the future is the intent. What I want to do is take the search that generated the data in the first place and automate that through something like Kafka. Take those results and put them someplace I can get at them, and then use a notebook automator to run the routine over and over and over again with new uncontrolled data every time I get it run from it, and then just have the results sent to a human. I'm assuming that this won't be necessarily good enough for static detection yet. But maybe it might be over time. If I can get this more dialed in, then I might be able to just have results sent directly to Glass for our IR people and just cut me out of it entirely, and we'll just have a very good static detection on it. So time will tell on that one. But for right now, I just kind of want to use this as a hunting technique rather than a detection technique. So to sum up here, I love not only effective solutions, but when an effective solution is also simple and intuitive and easy to share, those are my favorite kinds, because not only can I share this, but what I'm really hoping is that other people are going to be able to take this and go, oh, cool, I know what else I can do with this. Take it. I love it when people can take good ideas and take it to the next step. So that's why this wound up being such a cool thing to talk about. Think about what we might do next steps too. So like I said, I'm trying to, my intention is to be able to automate both the data collection and ingestion and analysis. What else might be something cool we could do with a technique such as this? Maybe there are different machine learning techniques that might be useful for finding obfuscated PowerShell. There probably are. This just happens to be one that I've been kind of running with and using. So that's why I wanted to share with everybody. And the cool part about this is it's pretty much repeatable on demand whenever you want it. As long as you can get new data, as long as you can keep your model trained and run, you should be able to feed data to it pretty much however often you want. So because of all this stuff, this is something that can just directly improve your security posture. This is something that you can get value out of right away, which is my whole intent of sharing this with the larger group today in the first place. And that's kind of my charge for everybody else here. So I would love for people to go try this stuff out, test it out in your world. Let me know how it goes. I love when people hit me up and go, hey man, I tried some of your stuff and it worked great. And not only that, but I may do this too. That kind of stuff makes my day. I would love to hear people trying this kind of stuff out. So check it out. It's at github.com/target-threat hunting. While you're there, check out all the other stuff in the /target repo made by a bunch of my very cool and brilliant colleagues. We've shared a lot of really fun things, really interesting things for the world. There's some great tooling in there, so go check that out. We've made it all available to the world, and we love to share this kind of stuff with other people. So that is my talk for today. So thank you again, everyone, for attending. I really appreciate everyone taking their time to come and hear what I had to say today. Please enjoy the Sense Threat Hunting DFIR Summit for 2022. There's some amazing speakers here. I'm really looking forward to hearing from all of them. And feel free to hit me up. Send me an email, hit me up on LinkedIn. I love to talk about this kind of stuff, so I would love to hear from everyone else. And that is what I've had to say for today. So thank you again, everyone, for your attendance today.